Okay, welcome everyone to this webinar related to FEFLOW groundwater modeling. To begin with the presentation, we have an agenda, and this agenda, we will start with some announcements. We have an introduction for all of those who are new to FEFLOW, and then we will focus on the topic of this presentation today, which is about different methods of modeling groundwater flow with FEFLOW. So we'll present four options how to simulate systems, so confined aquifers, or unconfined aquifers, or a mixture between these two types. We will have a live demonstration that you can see how this works in the software. Okay, so to start, the major announcement that we have today is our FEFLOW International User Conference. We will have this year again the FEFLOW conference in person. It's a conference which will take place in Hamburg, Germany, between the 8th and the 11th of October of this year. So the conference already has a website with a lot of information. If you are interested to join this conference, please visit the website. You will find information about the venue, about the different keynotes, speakers. We will have a full day of very interesting training opportunities, workshops, and of course the users' presentations. If you would like to submit your scientific contribution to the conference, the submission of abstract is already open. You can submit your contribution via the form. And if you would like to receive information about the conference, there is also a form to get in touch with us, and we will post you with the different updates and information of the conference. Second announcement related to this webinar. So recently, at the beginning of the year, we released a new self-paced training course. These training courses are for free, available. You just need to go to our website, the link that is available here, register, and this training course give you an extension to what I'm explaining you today. So I'm using the same exercises of the self-paced training course to demonstrate a few things. But of course, due to time limitations, I cannot explain everything what is in the course. So if you would like to expand more information about how FEFLOW simulate the flow processes, I would recommend you to go to this training course. If you are already working with FEFLOW and you would like to improve your workflows and create your FEFLOW models in a faster manner, even we have a new module is called PyH SMH. That stands for Python Supermesh, which allow you to build from a Python scripts entirely a full supermesh into called the mesh generator, set the number of slices, layers, and then with the existing methods that we already have in Python, you can complete the parameterization and run the model. So this is really a nice training course which demonstrates the full workflow from zero until simulation run and results using a Python script. So if you know something about FEFLOW already and you would like to explore of these possibilities, again, this is a free self-paced training course. Just click on the link and you will have access, or you will be prone to the registration form, and then the accesses will come in the next days. Okay, so FEFLOW. So FEFLOW is part of the DHI family of different products, so what we call the mic family. And FEFLOW already comes together with a number of products for surface watering in 2D or in 3D, Mike Sheep for catchment hydrology or integrated catchment hydrology. DHI also has products for urban water modeling, Mike Plus, river modeling, and so on. FEFLOW is not a new software. It's already existing back in the 70s. And DHI keeps developing this software at a yearly basis. So we will have an update, by the way, the next week about FEFLOW A1 update 2. This is basically some maintenance of the software. We'll have another update later in May and a major upgrade A2 in November. So together with the FEFLOW conference, we will come and offer a number of different new features and workflows. So if you haven't used FEFLOW A1 so far, and I would like to highlight a few of the things that we have been working in the past. So we have a new integration with CAT. possibility to manage and handle wells in groups and apply some operational rules. If you are working in the geothermal sector, we have a lot of improvements on FIFLO for those applications, for connecting the wells, creating open loops, closed loop system, etc. We have usability improvements for all the users. So the way how you handle your measurement data, if you would like to compare data with the model results, we have reviewed the workflow. This has been improved significantly. The Python interface that I was mentioning in the self-paced course, and we have also more methods for handling 3D and structure meshes. So FIFLOW comes with three core values. Our ideology is all-in-one solution. DHI developed the software, GUI, but also develops the engine. So we are 100% independent, and we develop what we want and we think that is valuable for the user. So we do not depend in developments of third-party components. FIFLOW has been decided to save the time and boost the efficiency. We have a number of methods in the graphical interface to do this. So a lot of keys, connections, or workflows, but also a lot of methods for handling 3D data, geological softwares, but also programming interface to speed up many workflows. And our third major core is the extensive visualization. There is no software, groundwater modeling software in the market that has so extensive visualization like FIFLOW. Together with this, we have a number of processes that we solve from flow and mass transport, variable saturated flow. I will talk today a bit about this. Contaminant transport, groundwater edge, heat transport, density, and chemical reaction. That will be the topic of other webinars in the future. So together with these processes, we have a number of technical methods and structure meshes, different numerical methods. So we are improving the solver and the different schemes for calculating in a regular base. We have an interface to PES for automatic calibration and certainty analysis. Every free-for license comes with technical support. Have a lot of training courses, academy free courses, instructor-led courses, online courses, and even if you work with ModFlow, we have a simple tool to integrate your ModFlow models into FIFLOW. That is only for the case of ModFlow 6 version. FIFLOW has been designed for working in different cases, from so simple box models to regional models. So that's one of the advantages, and one is also one single interface for all the different packages that we have. Just going quickly to the different interface. So the interface allow you to set up the model, run the simulations, evaluate your results. Everything comes into one single file, the .fem document or the .dac document for the model results. So you don't have to take care about text files and all these different stuffs, because everything is inside the proprietary DHI FIFLOW file. The interface can be customized. It gives you also some hints and tips about. So we keep this interface changing and updating. So now, for example, in the release or patch will come in the next week, we have review the way how the terminology, how we used to work for geothermal system. So we have explained it, make it more intuitive. So there are no more tooltips. So these are minor changes, but it makes quite easy the life for the modelers, because you directly from the GUI will know what exactly means if you choose this parameter or the other one. We have a number of workflows, and depending on the way how or the data that you have, we can help you. So if you start from 2D, we can help you to create 2D meshes, extrude the model, doing interpolations, and create the 3D geometry. Other users will have 3D geological sets, so we can import this geological set and build a 3D super mesh, and from here build a 3D structure mesh. So these are different possibilities that can be combined and used depending on the data that you have. So we want to offer multiple workflows, because there is no one single workflow for covering all the cases. Every FIFLOW license comes with a PES interface, with a FIPES. It's our optimized interface for FIFLOW models using PES and PES++, where you can do model calibration and certain analysis, but also more complex things like Monte Carlo analysis, iterative ensemble smoother. We can do parallelization directly. You can parallelize your FIFLOW runs using all the cores of your machine, or distributed And even nowadays, DHI has his own cloud infrastructure, so we can deploy all these hundreds of model runs to the DHI cloud if it's needed. And few examples of visualization that you have a feeling what is possible. So cross sections, 3D clippings. File format is an important part of our workflow, so we try to offer and extend the number of file formats that we are supporting each version. As I was saying before, we extend the capabilities of CAD, supporting the latest file formats in CAD, but also the WG files, so we can extend more things if you believe is required. So I'm always keen to hear and get this feedback from the users. And we have a flexible programming interface, which allow you to do a number of things. This is an interface that is already exists since more than 20 years, so it's really quite robust, available in C++, in Python, and in Python has been extended significantly in the last 10 years, including now the possibility to call mesh generators, create 3D models directly with a single Python script. Okay, and with this, I would like to jump to the topic of this webinar today, and is about groundwater flow modeling. So what are the different formulations to solve the flow equation in FEFLOW? So we have multiple methods, and I will start from the most simple to the most complex, and then through the exercises, we will see what is the impact of the different options and switches that I'm mentioning here. So one option is when you solve the groundwater models in 2D or in 3D, it's called phreatic. So you say, my system is unconfined, and in unconfined, I have multiple methods. One of these methods is called phreatic mode. Phreatic mode is a simplified method. If you go to the white paper or FEFLOW book, documentation, this is called pseudo-saturation. Pseudo-saturation is because it uses a simplified way to estimate the saturation in the elements. And this simplified way depends on the water column or the water depth and the thickness of the element. So it's a linear function to estimate how much water I have in the column and what is the portion of water in respect to the thickness. Based on this saturation, on this pseudo-saturation, we downscale the conductivity because we are in the unsaturated zone. We want to represent the fact that now the flow, the groundwater, the flow moves slowly compared to a fully saturated system. And this is simply a scaling factor of the saturated hydraulic conductivity. However, there is a situation where here if the water table is below the layer or the or specific element, the column of water is zero. It's not zero, but it's in this case, in the example, it's zero. So we cannot handle a zero division. So we need to take some assumptions. And as it happened in nature, there is a minimum on a residual saturation in FEFLOW. It's called residual water depth. And this residual water depth is assumed to be 1 millimeter by default, but can be changed by the user. So FEFLOW will calculate a residual saturation RWD divided by the thickness of the element, and this will be used to calculate that minimum hydraulic conductivity. So the advantage of this approach is that it's really simple and it's very fast. So if you take a 3D model with some complex parameters, a steady state will run very fast like this. But it has the disadvantage that is a pseudo-saturation method, which means that we know that changes of saturation are not linear, so you are overestimated or underestimated some processes depending. Second disadvantage is we have a global parameter for the residual water depth, which means that you need to be careful with this parameter, especially in cases where you have discretization of the layers, which could change significantly in some part of the model. So if you imagine to take the layer 1, where you have at the beginning, let's say this element 1 meter, but then suddenly the same layer, because you are interpolating in FEFLOW, change to a thickness of 100 meters. So this, although the water table could be just below the layer, so you could have different values of saturation. So you need to be careful about these cases. There are solutions. The more simple solution is to subdivide the layer with more slices. So we are reducing this dependency of the discretization. It's also very simple to solve problems of convergency with this method. The major issue of not converging is that the residual water depth is very small, especially in the case that I was mentioning where you have 1 millimeter with a layer of 100 meters. So then you need to increase the residual water depth or subdivide the layer. The second option is called free and movable. And as the name say, free and movable because the layers will move. You will have a definition which assumes that the top of the model in FEFLOW, the surfaces, the two surfaces which define a layer are called slices. These slices, in this example, I have 3 layers. I have 4 slices. Here we can see the 4 slices. The 4 slices will depend with the location of the phreatic surface, with the water table. The assumption to solve the problem is that the slice number 1, so the top uppermost slice, is exactly the location of the phreatic level. So the location with a 0 pressure surface, which means if you have a drawdown because you are pumping the system, you will see that your model will collapse. If you inject water or you recharge the system, your water table will rise. Therefore, your system will also extend your domain. So this has obviously some consequences, and the direct consequence is on the parameters. So if you imagine we have 3 layers with different materials, the materials could change quite significantly. We can have some sand and we can have some very low permeable materials below. So if we move the water table and if we collapse the model layers, so there will be an average of these layers. So there will be overlapping of the layers. So FEFLOW use here a volumetric average and then check what is the volume being overlapping in layer 1 and layer 2 per element, and then come out with a weighted hydraulic conductivity or weighted hydraulic parameters. So that's actually the one of the major disadvantages of this method. The advantage is that is very fast again to solve in cases where you are simulating very large regional models where you are not much interested on looking the details in the unsaturated zone. Then the method is nice because it will ignore the unsaturated zones and then it will solve and give you a major distribution of the water table. In the practice, so many users combine these methods. So you can get the first estimate of the water table by free and movable, and then you check things, and then you can change back to the phreatic approach where the layers are fixed and then do other calculations if it's required. Okay, and during the simulation, you will obviously see these changes of the conductivity. If you are saving the result files in our DAC file, you will also observe these changes of the conductivity being stored in the DAC file. So a disadvantage of this method is we mentioned already the averaging of the material. The second is if you have very heterogeneous systems, so you wouldn't like to go for this method because it's going to average some of these properties and it's going to represent not really what you want to model. If you have multi-layer wells, these are special boundary conditions for 3D models. Your multi-layer well will also change in length, so you need to be careful with this. So you need to really evaluate whether this method fits or not for your parameters. And then we have these two base methods. Let's go back to the first one, what is called phreatic. And now we start adding a number of special cases. So we have these 3 possibilities. Either the system is fully confined, easy. So we solve the flow equation with a given hydraulic conductivity and heads. If the system is unconfined, we also solve using the phreatic option. If the system is partially confined, so confined, unconfined, so here we have unconfined and this part is confined. So you need to specify some treatment. So how do you would like to to solve these problems? There are two options. So for the 2D horizontal case, but it's really the same for 3D cases. So in the first case, we have here, if you see the yellow line represent to the phreat, not to the topography of the system. The blue line in dash represent the phreatic surface, so the water level. So here we have the system which is unconfined, so no problem, we solve it with the phreatic. Here we have a system that is already confined, so the pressure is higher than the elevation of the model. The default option is called unconstrained head. Unconstrained head means that FEFLOW will basically extend the system and model. So extend the reservoir and keep model and doing the typical job. So nothing special. The second option is called constrained head. Constrained head means that the water table will be capped with a reference or with a threshold of the topography, the line in yellow. So the phreatic surface will exactly follow the elevation of the topography. How do we do that? Internally, FIFLOW sets a constraint, so it can set a boundary condition of hydraulic head, a constant value of hydraulic head equal to the elevation of the topography. And this head obviously will change node in each of the nodes depending how the topography change. This is a head. The fixed head could create an inflow or outflow. You could also prevent inflow by ticking in this auction. So which means that it will set a constraint of heads, and then if for any reason the water table drops, so let's say if the water table drops a little bit in this area, but you still have a head on the top, the head could produce infiltration, so inflow. If you would like to avoid that case, so you can simply activate this auction. So the question now comes is, so what is happening with this water volume? So what does FEFLOW with this? So basically this is removed from the system. Of course, you would like to know what is happening, how much is it. You can open the array budget panel and see how much water leaves and what is the rate in liters per second or cubic meters per day leaves through this location of the system. You can also display the location of this boundary node and see what are the spots where this process is happening. So you can say it or see it in a way as a very simple estimation to calculate what is the runoff. A typical example will be with groundwater flooding. So you have a rise of the water table due to some events which happens and infiltrated in another parts of the domain. So water table is rising, and you will have a rise of the water table like this. And if you would like to estimate what will be the flooded area, so you can also use this approach, and how much will be discharged to the overland could be also estimated by this simplified approach. The same method is applicable for 3D. This is just the same explanation. And now we have the opposite case. We still solve it with phreatic, but now maybe you have a 2D model, you want to simulate only a 2D system, unconfined, and for any reason, what is happening is that the water table goes below the bottom of the model domain. It could be a 2D model, but could be also a 3D model. It really doesn't matter. So this part, so this like looks like a triangle, it's is unsaturated. So how do we solve the flow equation in those cases? So we need still to have a conductivity or a transmissivity, and the value used will be a minimum value which corresponds on this residual water depth, what we were discussing in the previous slides. Alternatively, you can say, okay, I would like to have a very confined system. So my water table will not drop below the bottom of the domain, which corresponds to the yellow line. So I would like to create a thin layer of water following the shape of the model domain, of the bottom of the model. And the thickness of this tiny layer will be exactly the size of the residual water depth. So these are the two cases that you have. Depending on your applications, you will need to go for one or for the other. How do you solve multi-aquifer system? So that's also a very typical question. So I have now this explaining these two options. How do I solve the cases where I have phreatic systems? So we have unconfined, confined layers. So we can have even two confined aquifer systems. Um, the The most simple case to model this type of situation is using again the phreatic auction. In the phreatic auction, when you activate at the very beginning, we will see it in the live demonstration. And if you have many slices or layers in your system, FEFLOW will give you access to this auction called free surface, where you can say, I would like to have unconfined aquifers. And here you have slice numbers. Slices corresponds to the surfaces representing the top or the base of a geological layer or any layer in FEFLOW, and you can define whether the system is phreatic or this slice corresponds to a phreatic or a confined unit. Depending means that you do not exactly know what is happening inside this, so it will depend on the simulation of the result of the results of the simulation here. And if you really want to solve to define a specific confined configuration, so like in this case, if you know that this slice will be the top of the confined aquifer and this will be the other one, so you can also directly define it here. How is this affecting the solution? Is because if you are defining something that is confined, then FIFLO is going to work with the saturated hydraulic conductivity. For phreatic or for depending case, it's going to adjust the hydraulic properties depending on the saturation levels. Okay, the second part of this presentation goes in terms of unsaturated flow. Is really a very condensed part because we need more time to explain this. I will need another hour to explain you about unsaturated flow modeling. But to start a discussion, I bring this example. Say, okay, this is not an aquifer, this is a dam. So how do I model the infiltration or the seepage into a dam with FEFLOW? That is a typical case where you will use the Richards equation because we are capable to calculate the unsaturated flow laterally, but also vertical. So we have the 3D representation of this. For this, we use the famous Richards equation. It's an old equation back to the 1930s, which describes the relationship between saturation connected to pressure head and as a function of time. So this is a change of saturation over time, porosity, and this equation we know we have a conductivity, saturated hydraulic conductivity. We have a conductivity factor which depends on saturation. So when the system goes dry, this value is also reduced and downscale the conductivity. And we have a gradient, we have a pressure gradient, and we have a gravitational gradient. Since there are sinks and sorters, so pumping wells, recharge, there is a queue, and the whole system is equilibrated, so it's in balance, so there is a zero on the right side of the equation. So this equation is nice because reduce the whole problem to a single phase. So we don't need to do very extensive calculations. And secondly, benefit is valid for both bottle zone and saturated zone. So if the system becomes saturated, this part becomes one, and this also is a factor of one, so this becomes really the RC law. It's really simple to use. You need to have some parameters to indicate this relationship. We need two relationships. One is salt water retention curve, so the relation between saturation and pressure. Negative pressure means the reduce of the saturation. Reduce of the saturation means reduce of the relative conductivity. These functions are derived using these empirical models. So FIFLOW works with a number of empirical models. Van Genuchten, Brooks and Corey, Van Genuchten modify, etc. Or you use something what is called spline functions, where you can input some data in case you have some laboratory measurements, and then we will do a polynomial fit to this data and you work with this fit instead of the empirical curves provided in FIFLOW. And with this, I would like to jump to the live demonstration. So we have a model. As I say, this is the model that I use in the self-paced training course, which is free available for you. So the model is quite simple. So if it's a triangular mesh, so has a number of layers. We have boundary conditions. So we have only two boundary conditions. So we have a head on the left side of my screen and another head on the right side. The system has certain slope, so it's a hill slope, is done on purpose because I would really like to force that the phreatic surface in some locations of the model goes above the topography to really demonstrate what we have been talking before. So the elevation of the system is so about 2,000 meters and down to 800 meters, and the heads are changed from 1,750 meters hydraulic head, and on the other side is 950 meters. So these are the head values, and zero because we haven't calculated anything. And now we are going to look into the problem settings, edit problem settings. And in problem settings, in problem class, here is where you decide whether you go for a Richards equation or you go for a standard saturated or unconfined condition. So we are solving for simplicity steady state only. At the beginning, we will be working with this. And in the last case, I will show you the Richards equation. So we have free surface, and this is the list of slices that we have. We have 9 slices. You can change here the type of configuration or status, free and movable. Phreatic is the phreatic approach, the pseudo saturation, and confined is a confined aquifer. So if you like to simulate phreatic, we just simply do this. That's the most simple case, which means that there is one general groundwater table in the entire model domain, like is in our case. In case you would like to have multiple hydraulic conditions, like multiple confined units, you will need to change accordingly to the slices. Okay, so this is the unconfined phreatic. Here is the residual water depth. I change the default to 1 meter, and I'm solving the system as unconstrained. Top of the model domain and bottom of the model domain is unconstrained, which means that if the water table or the phreatic surface rise the topography, FEFLOW will basically extend the volume of the system and calculate naturally without any special handling. So press OK, and then it's stay run. So I'm using the Paradiso direct solver. You just take really few 2 seconds, and then the simulation results are available. So here we have the values of hydraulic head changing from the values that we set in according to the hydraulic head BCs. If I plot the water table, we can use the auction of the free surf, the pressure, and there is a zero ISO line. These lines visualize the location of the phreatic surface. So I can see that there is the water table here, and we have also a tiny location because is because of the head boundary condition. So we can also visualize the pressure. And this is the pressure distribution. So we have a negative pressure here. If I click the inspection, I see I have minus 1,780 kilopascal is a negative pressure, and it's in the unsaturated zone. And if I click here, now we have a positive pressure, so the system is saturated. Okay, so we have a water table that is above this location. Another way to visualize this water table is not much use, or not much known by users, but it's quite practical. We have the possibility to draw the surface, to draw a volume in 3D as a representation. So here you can, FEFLOW will encapsulate and tell you, okay, this is the location of the phreatic surface, and depending on the reference systems, it will draw a water table on top. So it's also quite nice to easily identify whether your system is oversaturated or not. This is called value surface. So we see that there is a high potential in some locations, but FEFLOW simply calculate. Let's take the water balances. Let's check with the panels. We have rate budget active, and we see we have only 2 components of the type Dirichlet. This means hydraulic head. We have an inflow and an outflow because there are no more boundaries, and there is a minimum imbalance of 0.02 liters per second. The 0.02 in respect to the other components of the balance, 7,092 approx, is negligible. So we can say that the system has closed perfectly the water balance. Okay, so let's try to do something else, and then let me check the system now to to constrain it. So to, sorry, to avoid, to make it quicker, I have already prepared the file. So I just simply open the files here. FEFLOW, we have phreatic constraint. So that's back to the system. So now it's the same model. We just now say constrain it, apply. Okay. We run it. Admit to save. No. It's gonna take also a few seconds, but it's probably a bit more than before because now we have additional constraints. There is a chart called head error history, error norm history, which tell you how many iterations FEFLOW is using for solving. So we have only 5 iterations. The default number of iterations is 12, and this error tolerance 10 to the minus 3. It satisfies the tolerance with this value. 5, 10 to the minus 4 is lower than what we're asking, 10 to the minus 3, and this was achieved after 5 iterations, therefore stop the calculation at this point. And now we can see that the water table change is a bit different because we are forcing to not have a water table above certain locations, which is the topography. If we look now, let's take a look on the pressure distribution. So we can see that here we have again negative pressure, which corresponds to the unsaturated zone. Then here we have the location of the water table. So this will be close to 0 pascals because we are enforcing the 0 pressure heads here, or a hydraulic head equal to the elevation. So if we plot the hydraulic head BC, you can see that FEFLOW has introduced automatically some boundaries here because in all of these nodes, the water table is above the elevation. So this is what I mean when you can identify what are these spots when the water table is rising. And then here the slope change, and again here there is also increase. So FEFLOW settings or not, because again the water table want to rise above the topography, but because of the rule we basically just set the heads here. Okay, so you would like to know how much goes into this part through the boundary conditions. It's quite practical. I think I have, yeah, I have this one runoff area. So which basically is the selection on the top slice only. And if I activate to current node selection and say active, it's telling me I have a negative value of 4,554 liters per second. So to enforce that the water table is exactly equal to the topography, FEFLOW needs to extract from this system this with this flow rate. So this will be your estimation of runoff. Obviously, this value will change if you have a transient simulation. It could increase or decrease depending on the case. Okay, next approach is the free and movable. I have the free and movable, and with this I need to hurry up because I see that I have some questions to answer. Again, same approach, we go to the free surface, and this time we say here this will be a free. Okay, look the shape of the model, and now if I press start, the system will collapse because we are decreasing the water table. Yeah, so that's the location of the elevation now of the slide number 1, because now this corresponds slide number 1 with the location of the phreatic surface. So that is the effects of solving the system as free and movable. So if you clip the model, so you can also visualize inside. So here we have a head of was 900 and something, and here we have another. So how is the gradient been happening inside the system? Okay, and the last option to show for today is the unsaturated. So I have the same model now running with the unsaturated system. For solving this in the unsaturated, we simply need to go to the main page, problem class, and switch to Richard's equation. This is a steady state. I have to say that solving the unsaturated, the Richards equation in steady state conditions sometimes is hard. Depends a lot on the combination of parameters that you have, on boundary conditions. So it could be quite often that it will not converge, but there are some tricks to get this, to solve this convergency. So one is basically running the system in transient for a long time and then see where is the water table changing or fluctuating. And having this knowledge, you can try to fine tune your settings to make it run in steady state. Okay, I haven't changed anything in the parameters, only Richards. If I uh, press the simulation, meanwhile it's running, you can see here that in the data panel now we have different parameters. So we have a saturation parameter. We're calculating in each of the nodes. So we solve a finite element problem. Each of the nodes has a saturation. The default saturation in FEFLOW is very small. So this is the value that is giving me 0.002. I have a this is a relative value. I have a moisture content, which is saturation multiplied by the total porosity in the system. We can plot again the water table here. No, this is the pressure, sorry. We can plot the water table and we can see that this part is unsaturated here. So as we were drawing before. One parameter that is quite interesting to review here is in the auxiliary data, you have relative permeability. Relative permeability has to be reviewed always because depends, this affect your solution. I haven't changed any parameter, and this is telling me a relative permeability factor of 10 to the minus 80. Back to the equation to connect the demonstration with the maths here, we have this Richards equation. This corresponds to the relative permeability or relative conductivity. So I'm saying that I have a factor of 10 to the minus 80 multiplied my saturated hydraulic conductivity. Obviously, this is a very minimum value and you need to correct. With this, I would like to mention that it's always a good practice to review default parameters in FEFLOW because these parameters are set to get solutions, but we never know a priori what you would like to do with the model. So that's why it's always important to review these parameters. So because the common mistake of the user will be start doing a calibration, changing the conductivity, a lot of things, but it maybe the conductivity was correct. It was basically a problem of the unsaturated parameters used in these settings. And with this, I would like to stop with the live demonstration. I would like to to thank you for your participation, and we will have a number of webinars in the next month. So please try to enroll if you find this information educative or interesting. So you are very welcome to continue joining on these webinars. And if you're interested in the FIFLO conference, please visit our website and then try to enroll if it's possible. Thank you for your time, and I wish you a very good day, afternoon, until the next time. Bye.